It's working.
Don't forget to record.
Oh, thank you. All right, perfect. And we are recording. So in this lesson, again, same thing as yesterday, what I was saying. The same rules and process apply as adding and subtracting fractions. We're just doing that with now polynomial expressions. Expressions are a little more complex than these standard fractions we're used to. So I know that you know this process, and I'm going to talk about it just a little bit more than usual because we need to figure out what I'm talking about as far as what is a special one. What is a special one? Okay. So same steps approach apply. You look to find the least common denominator. We'll have a few different strategies for that. And then really you do that by multiplying by a special one to make the same denominator for all the fractions. You want the same denominator. Can we add this without manipulating it? Not yet, right? It's 2/3 plus 5, 6. 3 and 6 aren't like denominators. We need like denominators. So who can see what the least common denominator will be for 3 and 6? 6. I always look to see the largest value of the two denominators and see, could I make the other one equivalent to that? So I'm just going to rewrite both fractions. I know 5, 6 is actually going to stay the same. We don't have to manipulate that. But 2/3, we're going to multiply by a special one, okay, a special one, in order to get that same denominator. Talk to your neighbor 10 seconds. I'm sure half of you already know it. So with your neighbor, what is this special one going to be? Pretty basic. And you'll see why I asked that question in a second. Exactly. Awesome. I think that is in your cards for the rest of your. So, who can tell me what is our special one, and why do we have to call it a special one? Yes, Luke.
Well, okay, this is mine. I'm going on a limb here, but is it 2/2?
I think you went on the right limb. It supports you. You will not fall. It's 2/2. Why do we call that a special one? Why I thought, or when I said that, how many of you said just multiply it by 2? Right? That is actually an incorrect way to see it, and it's going to hurt you when we get into more complex polynomials here. Because remember, the rule of manipulating the denominator also involves manipulating the numerator to change the fraction, to find an equivalent fraction. And we have this special one. 2/2 is a special one, right? X plus 1 over x plus 1, that's a special one. You can have an expression over itself. As long as it's identical, it's equal to 1. Okay, so it is a special one. In this case, 2/2 is our special one. We get 4 sixths plus 5 sixths, 9 sixths, 3 halves, done. So I'm not going to ask yet because there's no variable in that problem. So there's no restrictions. There's no variable, so there's nothing to restrict. All right, looking at the next one here, we're just building a little bit. You see it's pretty similar. But what would our lowest common multiple be in this case? Keep saying that. What is the least common denominator going to be in this case given these two denominators? 6x. So again, I'm going to set it up. 5 over 6x. We're adding to 2 over 3x, but we need another one of these special ones to fit here. Who can see that? What's the special one?
The same one.
2/2. 4 over 6x plus 5 over 6x. Now, am I going to add together 6x plus 6x? No. Once you find the common denominator, that is also going to follow all the way through. It's going to be the common denominator at every single step, unless you're able to reduce it by canceling it out by creating a special one. Okay, so let's see. We have 4 plus 5, we get 9. What can 9 over 6x reduce to? 3 over 2x. Okay. It does remain in the denominator because it was 6x in the denominator. So it's not 2/3 or 3 halves x, it's 3 over 2x. Okay. Now we have to start talking about something different. Look over here, and you at home can't. Still can't. That's okay, I'll block the glare. Variables we have restrictions to because when we have ratios, when we have fractions, you can't have what? A 0 in the denominator. You can't have 3 of 0 cookies. If you can, I mean, you're a wizard and you're going to make millions of dollars by making cookies out of nothing. But don't do that. It's a bad investment scheme. Therefore, 3 over x minus 8. What value for x can we not have in this case? 8. Because what happens? 8 minus 8 is 0. If you couldn't see that, if it was a little more complex, you could take that x minus 8, make it equal to 0, add 8, add 8. I mean, if it was more complex than this, of course. You'd say, well, x is equal to 0, that's when it equals, x equal to 8, that's when we get 0. So x cannot be 8. Let's look at our example over there, and what kind of restrictions should I keep in mind? What can x not equal?
0.
In this case, it's pretty straightforward. 2 times x. So if x is 0, then we end up with a 0 on the bottom. It's undefined. We can't have that. So in addition to putting the answer like so, you need to also include x cannot equal 0. That is the full answer there. On the quiz and assessments, if you don't put the restriction when there is one, it's going to be a pretty big mark off. Okay, so restrictions we'll get to. Next we'll get to more of the honors kind of component to that. But let's look at this last one now. A bunch of ways to deal with this problem. A bunch of ways. Who can think of a strategy? Just real quick. I'll even ask for another strategy. Santoshi.
Well, you could multiply like by each polynomial, so like 3x plus 3 times 6x plus 6.
Good. Like where you're going. And this is one way that you can always do. If you're confused what the common denominator is, you can always multiply the two denominators together. Because you know if they're multiplied together, each is a component of that new common denominator. Now in this case, that's actually a little bit more work. So that's good to be our first one. What's another way you can do this? There's tons of ways. What's another way? You can see another way. Jackson?
Can you just multiply by 2?
Over
2.
There it is. So I want the language. I know what you mean, but I want us to start to see this as we're not actually multiplying by 2. We have our fraction here, and we are multiplying by 2 over 2, which is our special 1. So essentially, you can never be wrong if you say, just multiply by 1, and you're not wrong. Right? Don't do that on the test. All right, so we end up with 4 over 6x plus 6 plus 5 over 6x plus 6. We know that the answer is going to have 6x plus 6 in it. Up here we get 9. We can think of the next step that we can do to get that a little cleaner. It's 9 over 6x plus 6. The 6x plus 6 is kind of the clue. Santoshi, what do you think?
Could you take out like 3? But like, no, not gonna work. I mean,
Let's take
you
more
could
out.
take 6. And
There we go. If we take the 6 out, we get x plus 1 times 6 on the bottom. And then we just then we reduce. I see what you're saying. I see what you're saying. Okay. So we end up with 3 over 2 times x plus 1. Now, is that our final answer? Will you get full credit if you just leave that?
No.
No. What do we think you need to do, Ellie? X cannot equal. What was it? It's 2 times x plus 1. If I put 0 in here, 0 plus 1 is 1 times 2 is 2. We need something else. How is inside this expression x plus 1 going to be equal to 0? Negative 1. 2. So if it works here, it will work here too. X cannot equal negative 1. If I put negative 1 right in here, negative 3 plus 3, 0. Put negative 1 here, negative 6 plus 6, 0. So the restriction works throughout. Okay. I'm going to go ahead and pull this down for a second. So just hold up. I'll bring it back up in a second. We're going to look at Desmos for a second because we're going to build towards graphing some of these rational expressions later in the week. And I'll look here at Desmos, and let's look over at our problem. If this is a function 3 over x minus 8, right? X cannot equal 8. When we're graphing, in order to express the restriction when we're graphing, we use what's called an asymptote. So you've seen asymptotes before. And I will relate it to what you'll see in calculus, because a lot of the beginning of calculus is talking about limits. What is the limit of a function as x approaches, positive infinity or negative infinity, or approaches one of our asymptotes, one of our undefined values. Because you can't have, I have the two functions here. You see you have the f of x equal to 3 minus 8, that's what we were dealing with. And I have x is equal to 8. And watch what happens. If I show the x is equal to 8, I have that green line there, right here. Right? Am I going to find that the function of 3 over x minus 8, is it going to cross that green line? What would it mean if it crossed the green line? Then there would be one solution where x does equal 8. Right? This line here is our asymptote, and when I put the other function in there, watch what happens. It's going up to that asymptote, but it's not touching it. Right? You see how that works? So when we have an asymptote, the function continues to get closer and closer and closer and closer and closer. So if this was more in the calculus realm of looking at this kind of situation, this would be the limit as the function approaches 8 from positive infinity. What happens? It goes up towards positive infinity. So that's going to be next year for some of you, or the following year for some of you. But when you get to calculus, a lot of asymptotes and how they are dealt with is going to be really important. So I will close that, and we'll do some practice problems. All right, we're doing pretty good. Let's keep it up. Number 1. First off, help me out. I need at least, in the least, I need these both to be fractions. So how do I change up the second fraction?
Make it 3 over 1.
There we go. X plus 1 is added. Now, Santoshi's original suggestion in order to find the least common denominator was to multiply the two denominators together. And that, in this case, is as well the best option. But again, we're going to bring in the idea of the special ones, because when I rewrite this, I want to think about it as I'm going to multiply this side by a special 1, and I'm going to multiply this side by a special 1. What's a special 1 on the left side?
1.
1 over 1. It's just what was in the denominator here. If I want to make the same denominator, I have to multiply this entire fraction over here by 1 over 1. This is going to then become a part of the next fraction, of the second fraction. So that's going to be x plus 1, x plus 1. See? That is the way you can make it work for every single problem. If you get confused, it may not be the least common denominator, but it will be a common denominator. So I do so, and I get 5 plus 3 times x plus 1 over 1 times x plus 1, which I'll leave there for fun. Okay. Oh, this looks great. Can I just cancel out the x plus 1 and x plus 1? Notice my sarcasm? Yes or no? Alan? No. 5 plus 3 times the quantity of x plus 1. That is the entire numerator. You can't decide I want to just cancel these out, because really it's the entire upper expression divided by the denominator. So when you have a polynomial on top, you can't just decide to factor out part of the polynomial and another value on the bottom. It has to be all or nothing. So if I look at this, I'm going to end up with 5 plus 3x plus 3 over x plus 1. We're going to end up with, let's see, 3x plus 8, x plus 1, and x cannot equal negative 1. Answer. Let's see if that applies, again, to the original problem. If x can equal negative 1. If we did have x equal negative 1, yeah, we get a 0 there. We're out. Yes, Jackson?
The first, like, 2 example problems, the graph, how did you figure out, like, what x could not equal? Just by plugging it in?
Good. So I look here, and it's 2x in the denominator. That's the key. You look to the denominator, because we know the denominator cannot be equal to 0. So then I can either just deductively reason, what do I plug in for x in order for it to be equal to 0, I'd have to plug in 0, right? We're trying to figure out what would make it equal to 0 so that we know not to do that. That's why I'm labeling it as x cannot equal 0, right? So here x cannot equal 1 because I've put a -1 there, or it can't be -1. That combines to give us 0. Can't have it. Okay, good question. All right, next one. What do you think we should do for example 2? I'm going to rewrite it. You can tell me the special ones. You guys are getting tired. I have to talk. You guys have to talk to each other for a second here. Oh, man. All right. We're going to have 2 special ones that we're going to multiply in order to find our common denominator. Talk to your neighbor. Make sure they know and you know that they know that you know. Okay. All right, who's feeling lucky or confident? Or lucky and confident? Hayden.
Well, the easiest way is to just do for the left one is x plus 2 over x plus 2. And then for the other one, 3x plus 1 over 3x plus 1.
Right. And we haven't changed anything from the original fractions. We've multiplied a fraction by 1. It can always multiply something by 1 and not change its function, its identity. Very good, thank you. And then we're going to go ahead and we'll just multiply these 2 together. I'm actually going to FOIL these out, but I need to also keep in mind that it's subtraction. Watch out for the subtraction. I know on the bottom I get x plus 2. I get 3x plus 1. I'll probably FOIL that out too. On the top, 2x times x, 2x squared. 2 times 2x, 4x. It's going to be minus whatever I get from this trinomial I'll create. 3x times 2x, 6x squared. Outer is going to give us negative 3x. Inner is positive 2x. So we get minus 1x. Positive 1 times negative 1, minus 1. The reason why I did that out first and left the expression in this quantity with the subtraction out there is now I need to go in and distribute that negative throughout. Okay, almost there. 2x squared plus 4x minus 6x squared plus x plus 1 over, I like FOILing, we'll just FOIL it out for fun. So we get plus 7x plus 2. Combine your like terms on the top, put your restrictions, and that's going to be it. I want you to finish that up for me. Go ahead and combine like terms on the top, throw your restrictions there, and then we'll bring it back in like 30 seconds or so. So I know this is on the bottom. Oh. I see now that the restrictions, remember you can pull the restrictions out anywhere along the problem. They will remain the same throughout. So we're going to look at, is there another place for us to find the restrictions? Because I'm not really worried about it, but I did make it a bit harder to see the restrictions. And in fact, we're going to finish it this way, but in general, you can leave them as binomials. That would be fine. All right. Negative 6x squared, positive 2x squared, negative 4x squared. We have a positive x, we have a positive 4x, plus 5x, plus 1. And I look at this, and I want to know what Gene's thinking. Gene, hand up.
Yeah, I have a question. So, what you got? So that's our answer, right? For homework what we have, so when we're doing this, can we leave it like that, or do you want to do it how we were doing it yesterday, and like maybe, find it?
Leave it here.
Yeah.
Here's the deal.
Simplify it too.
Right, and you know, I am going to go back and revert to the binomial. It's not incorrect, but I do like leaving in binomial, which I'm just seeing your point here that it does allow us to find what really quick?
The
Restrictions, because the top I really couldn't have left it in the mess of here's two binomials multiplied, here's a monomial and a binomial. I wouldn't leave it. I wouldn't leave those like that because I want to see what I can cancel out as well on the top. But on the bottom, yes, let's leave them as binomials. Good idea. X cannot equal what? Negative 2. X cannot equal what else? If you can see that, it's good. One person saw the fourth period. Good job. Negative 1/3. Because you plug in negative 1/3 here, you end up with negative 1 from that 3x. Plus 1 is 0. Over here, negative 2 plus 2, 0. Can't have those done.
How would that look?
How does this look with the graph?
Yeah, with 2.
You want to see? Obviously, you asked. Let's see. Hey, it was a good thing. I want to see that too. It's going to take a second to write in this. Put this big. You know what? I'm going to do it without even the restrictions. What I'm going to do is, yes, I need this visible. Get in front of the video. Sorry, I almost looked like I hit you in the video. He wasn't hit. Okay, these are gone. You guys are so quiet today. Not? You're singing right now?
Yeah. Actually, no, it's not raining outside. I can't listen.
It is kind of one of those days because of the rain. It does not feel. Get out of there.
I only sing when it's raining outside.
You only sing when it's raining outside. Thus, you're singing in the rain.
Yes.
Okay. With an umbrella.
And my tap shoes
That's awesome.
Are you Tom Holland with that? Sounds like a nice time.
All right, here we go. We have the graph of. Oh, it's beautiful. It's beautiful. What were our asymptotes again? We had x is equal to negative 2. We have x is equal to negative 1/3. Like we have. Good job, Dean. So we have one asymptote here. You can see a really peculiar looking graph here. And rational expressions have weird graphs. There's different symmetric things that are hard to see here. Here's the other asymptote. So you see that this one's confined between the two. This one never touches but goes down. Let's see what happens when we go out. Let's see what it looks like. And it looks like an X. That's weird. All right. So does that affirm our asymptote conjecture? Excellent.
The dividers the line makes the red line, the blue line makes the red line go up, and then this one's going down again.
Because as the function approaches that asymptote from different sides, it has different behavior. And you could figure this out by using what I mentioned, the calculus and limits, or you can just plug in points as you get closer and closer and closer and closer to that negative 2. You plug in points, you'd see what happens.
Go like that.
Well, there's only two options it could do. It could go towards, from this side, it could go towards our red asymptote and go down, or it can go up. In this case, it goes up because of the nature of the function. And that's a little hard to see right off the bat because we have a negative a, we have a trinomial over two binomials. There's a lot of complexity in it. Graphs will look different every time. But as they approach the asymptote, it's what happens as it approaches from positive, what happens as it approaches from negative. That's what you always assess. So I'm glad you did that. I'm glad you asked that. That's all. Good job, Gene. Invisible starburst. Worthy. Okay, I am not going to do this entire problem. I'm going to start us looking at it. And what is a strategy when you see one of our denominators is a trinomial and what is a binomial? What could we do, Andre?
Factor.
Factor it. Let's do the x method. Okay. Negative 6 and negative 1. What multiplies give you negative 6, adds give you negative 1? Okay, good. So we have x minus 3. We have x plus 2. Wow, that's kind of nice. Because look, we have something in common. These two are the same binomials. So essentially, I know from this, I've replaced this trinomial with these two binomials. The first fraction is ready. The first fraction is ready because we have x minus 3 and x plus 2. On this side, what is going to be my special one that I need to multiply the second fraction by? Yeah? Yeah. X plus 2? X plus 2? From there, I know, I'm confident you guys will be able to work that out. This is just a binomial. FOIL that. It's 5 minus that, distributing the negative, whatever trinomial you end up with. The denominator is going to be this, which tells us my restraints. X cannot equal. X cannot equal. Since this is going to be the denominator, because both of the fractions have it, yes, we're going to end up with x cannot equal 3, x cannot equal negative 2. Good. So my answer, this would be the restraints, but you'd have to do a little bit of work, obviously, distributing that, combining like terms, but that would be it. So I'm going to shortcut it, because we spent some time on the extra asymptote problem. All right, any shout-outs, any important information we need to convey to the public at large? My viewers in Brazil.
Lincoln's birthday was yesterday.
If you didn't catch it, Lincoln's birthday was yesterday. We did a devotion. We did a Guns N' Roses. We could all go out by like singing "Take Me to the Jungle."
No, I think we're good.
Santoshi. All right, let's do whisper. A creepy whisper. Subscribe on 3. 1, 2, 3. We're creepy.